Okay, everybody, this is section 2.1, but I got to make sure this thing's going to be lined up so you can see everything I want to produce. Show you here. I try to show you everything on the board over here, but there's a lot of graphing we got to do here, so I'm trying to get it all lined out here. Chapter 2 is all about quadratics. So the last chapter we talked about constants and linear functions and quadratics and absolute values, and we're going to focus exclusively on quadratics for this chapter. That's the y equals x squared for a parent function. The transformations that you already learned are going to hold true here, but there's a few other things you got to be able to do. You're going to have to be able to graph them and use them to solve problems, and so there's a few details we've got to cover here. One of the very first ones that I like to call a quick graph you won't find in any book, so you may want to review what I'm about to show you here when it comes time to actually graph a quadratic. First of all, if you take a look at the parent function, y equals, or f of x equals x squared. If we were to plot some points here, there's some things I want you to notice about the y values. I'm going to start at 0 rather than -3 like I usually do. I'm going to go 0, 1, 2, 3, 4, 5, 6. That's probably good enough to show you the pattern. I put these numbers in one at a time into the parent function. So if I put 0 in for x here, 0 squared is 0. 1 squared is 1. 2 squared is 4. 9, 16, 25, 36, and so forth. I want to show you what these things look like if I were to graph them the normal way with just with these points right here, just by plotting points. If I were to plot 0, 0, and then 1, 1, and then to come back here and plot 2, 4, I'd have to start here at the origin again, and I'd have to go over 1, 2, and up 4. 1, 2, 3, 4. And then to plot the next point, which is 3, 9, I would have to start back here at the origin and go 1, 2, 3, and then count up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And if I wanted to do one more, I'd have to start here at the origin, and I'd have to count over 4. 1, 2, 3, 4, and then I'd have to count up from here 16. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that's a lot of counting. Takes a long time. Seems kind of silly. And you're likely to make mistakes if you're not really careful counting, especially on the little tiny graph paper that I gave you. Also observe that in connecting these points right here, I'm only getting 1/2 of the parabola. But the cool thing about a parabola is it's symmetric. Once you've made the turning point here at the vertex, this point 1, 1 here reflects across this axis of symmetry, we call it. It's called an axis of symmetry, which goes, oops, that wasn't very well drawn, which goes right straight through the vertex like this, and all the points on this side of the parabola reflect across that axis of symmetry on the other side to get the rest of them. It's not very hard to do. So this one, oops, too far. What do I mean by mistakes? So this one went over to 1, -1. This one, if you count straight across to the axis, you count over 2, and you count 2 more and plot it. This one went over 3, so you count 3 more. This one was over 4, you count 4 to here, and then 4 more, and you get your symmetry points, and they're not very hard to get. So what I'm saying is, if you could get one side of the parabola, all you have to do is jump across the axis of symmetry to get the other side without having to do this. There's something else to note here that will not be shown in your book. It's not taught in any book that I've ever seen, but it's something to notice that I found out in, I didn't find out, we discovered it in a class I was in college. I want you to look at the y values here. First of all, well, one thing. Notice that the x's are only incremented by 1. This is 1, 0, 1, 2, 3, 4. Very straightforward, all one gap. There's just 1 in between each one of these. But notice these. From 0 to 1, the gap in the number line is 1. From 0 to 4, it is 3. From 4 to 9, it is 5. 9 to 16 is 7. 16 to 25 is 9. 25 to 36 is 11. And the next gap will be 13, and the next gap will be 15, and the next gap will be 17, and so on. It's the odd numbers that separate them. So I want you to consider plotting this graph instead of the way I did it a few minutes ago. I want you to think about this. Find the vertex. Well, the vertex of the apparent function is super easy. It's right here at 0, 0, because when x is 0, y is 0. So if you can find the vertex, then to graph this, instead of always returning to the origin to graph the next point, here's what we can do. We go out 1 and up 1 to plot the point 1, 1. But keep your pencil here at 1, 1. Then count out 1 more because that will get you to the 2 for this point. Because it always goes out 1 more. X goes 1 more than it was before. And then count up that difference, which is the next odd number. 1, 2, 3. Then come out, and the next odd difference is 5. Instead of coming clear back to here and counting out 3 and then counting a full 9, you're already out 2. Come out 1 more to get to 3. You're already up 4, so count the next difference, which is 5 from there. 1, 2, 3, 4, 5. Go out 1, count 7. 1, 2, 3, 4, 5, 6, 7. You can get your points on here a lot faster if you recognize these differences and just count that much more after you count out 1. Once you graph those, you grab the symmetry points. Out 1, well, you just jump across the axis of symmetry. Get this one over here, and then you can sketch your graph by carefully graphing these. Now, one thing to note, when you actually turn the corner right here, you should never make it a point. There are no points in a parabola. Just make a sharp turn, but not pointy sharp. This should not be a point. It should be a nice smooth curve coming through here, just so that you know, so that it doesn't look like some sort of a absolute value function or something. Now, most people, after they see this, they go, now what? They do that again? So I'm going to show you one more time. But I'm going to go faster this time to show you how it might work on your paper once you get used to it. Find the vertex, which is not always going to be 0, 0, but it is in this case. Then you go out 1, up 1, out 1, up 3, out 1, up 5, out 1, up 7. Just like that quick. This is the axis of symmetry, which it is, not very good drawing. Jump across, get those. You've got your parabola immediately. Now you might say, okay, well that's real great, Miss J, and I can do that if it's the parent function. No, it works for all parabolas, and I'll show you the differences here in just a second. Let me get this erased. Well, you know what, I think I'm going to leave this up here, this one, so that we can compare to the parent what these others look like. So put this vertex back in and carefully graph this thing. It's about the third time I've done it. Try not to make this thing down here too pointy. Round it out. Okay? All right, so there's your parent function. What would happen if I had this parent function, which is f of x, and I had a transformation of f of x called g of x, which is what we're used to doing, equals 2x squared. All that would mean, if we were to put some x's and y's on this, all that would mean is that when we plug in a value of x right here, we would still square it, because we have to do squaring first in order of operations. You would first square it and then double it. So 0 squared is 0, times 2 is 0. 1 squared is 1, times 2 is 2. 2 squared is 4, times 2 is 8. 3 squared is 9, times 2 is 18. We're getting pretty big pretty fast. I don't think I want to count much higher than that. So if I graph this thing with some blue chalk so that we can compare it to this one, notice that when we put x in and y, x is 0, y is 0, it's still going to be the same vertex. We haven't moved it anywhere vertically or horizontally. Still starts right here. But notice that if I plot the first point, I'm going to go out 1 and up 2. And the next one is 2, 8. I'm going to go from the origin. I'm going to count out 2 and up 8. 1, 2, 3, 5, 6, 7, 8. I'm going to go out 3 and up 18. Wow, that's going to be quite a count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, if we jump across the axis of symmetry like we did before, you can see that if I connect these blue ones, I get a vertical stretch. I'm paying more attention to the specifics now than I did in chapter 1. So that would be a vertical stretch of 2, but here's what I want you to notice in the numbers. These all increment by 1s, just like before. But the difference between 0 and 2 now is 2. And 2 and 8 is 6. And 8 and 18 is 10. So I'm going to put these in here. So from 0 to 2 is 2. From 2 to 8 is 6. From 8 to 16, or from 8 to 18 is 10. Here's what you notice. 2 is 2 times 1. 6 is 2 times 3. 10 is 2 times 5. So we should be able to expect the next gap to be whatever this number is. Doesn't make any difference. It's going to be 2 times 7. See these guys right here? Those were the differences in the parent function. 1, 3, 5, 7. So in other words, folks, to count this without having to make this table every time, which takes a long time, to count this when out, you would go from the vertex, out 1, not up 1, but twice 1, which is 2. Out 1, right to there, not up 3, which would be the next odd number, but 6. Out 1, not up 5, but twice that, 10. Okay, so it's a little quicker. It's a little quicker count because you can stay on the point you were on. This is the thing that we took all of the odd numbers and did to it. We doubled it. So we still remember these numbers, 1, 3, 5, 7. And every time you go out 1, because you're going another x out. It's just one incremented by 1s. So to graph this daughter function here, 2x squared, you do it just like you do x squared. You start at the vertex, and you go out 1, not up 1, because that would be the normal first count. So you go out 1 and twice that, which is 2. You go out 1, and the next odd number is 3, so you go twice that. The next odd number after you go out, you double that to 10 to get this. Now let's try a vertical shrink. Let's say we had the function h of x. That was equal to 1/3 x squared. This multiplier on the outside of the function is going to vertically stretch it or shrink it. In this case, a shrink because 1/3 is less than 1. You knew that. So let's do this one in white. And let's see if we can make this work without drawing the table of values. Let's see if we can make the whole scheme work right here for this 1/3. So since there is no transformation up or down, right or left, because there's nothing added to x, there's nothing added on to the end, this is only a vertical shrink of 1/3. So here's how we count it without making the table. You start here at the vertex, which is still 0, 0, since when x is 0, y is 0. And you go out 1. You always go out 1. But you only go up 1/3. Like that. And I know you're going to have to zoom in on your screen probably to see that. But I started at the origin and I went out 1 unit. And I only went up 1/3 of a unit. I'm going to leave my pencil there. I'm going to go out 1 unit and go up 3/3, because the next odd number after 1 is 3, and so I take 1/3 times 3. Well, 1/3 of 3 is 1. So from this 1/3 point, I'm going to go up to 1/3 right there. From there, I go out 1. The next odd number that I haven't used yet is 5. 5/3 is 1 2/3. Here's the 2/3. Here's the 1. The next one's going to be 7/3, and 7/3 is 2 1/3. So I go out 1 and up 1, 2 1/3. And then I carefully jump across the axis of symmetry over here and get them at the same height. Like that. And connect those. And that will allow you to draw the graph of a vertical shrink or stretch. See, that's a shrink because it got wider. Vertical shrink or stretch based on the odd numbers for your y values. Okay, you won't find any of this in any book. So I'm going to be using this from now on. So I hope you have got the scheme down. Hopefully after seeing it several times, you'll really get it to where you can use it really well. So if you will look at example 1, and this one we're just going to talk about moving it around. So I'm kind of switching gears here. We're not just going to graph vertically stretched and shrunk parent functions. We're actually going to try the transformations that you learned last chapter, and we're going to apply them exclusively to quadratic functions. And there are 6 transformations, and I think I better remind you of all of them before I actually do this example. I'll come back to the parent function. I want to write this down. You may want to write it down too. For any function that we wish to transform, if f of x equals something, then f of x plus h will move that original function left h units. Whatever this is, because this was a plus sign, this will move it left. If I have f of x minus h, that will move it right 8 units. This is all review, folks. 8 units. so this is right and left. If I want to go up and down, then I would take f of x and add k. That will move it up k units. If k is 3, it's going to move it up 3. If I take f of x and on the outside of it, I subtract k units, it will move it down that far. You know this. Just reviewing with you. We have reflections in the, let's say in the x-axis. That would be f, or negative, f of x. Whatever this original function was, when the negative's on the outside of it, applies to the entire function. It's going to reflect in the x. And of course, if it's inside, it will reflect over the y. If I want to vertically stretch it, I think I better come over here. I hope you can still see over here. If I take this original function and I do this to it, let's see, a, f of x, that will, well, it'll vertically stretch if a is greater than 1. So if this is bigger than 1, it's going to stretch it. It'll be a vertical shrink if a is trapped between 0 and 1. In other words, a proper fraction. And we got to do the horizontal stretches and shrinks. If I have f of a x, that's a horizontal shrink of 1 over a, because remember, we have to deal in reciprocals here. And let's see, it's a vertical shrink of 1 over a if a is greater than 1. F of, let's see, I'm not going to do that one. I'm going to stick with f of ax. It will be a horizontal shrink of the reciprocal of a if a is between 0 and 1, a proper fraction. So those horizontal stretches and shrinks are kind of rough. It helps to see an example. But you may want to stop your show and maybe take a picture of this on your phone or write it all down or something. But these are all the things you have to deal with in a general way that we're going to talk about here in just a few minutes. Okay? So we're going to talk about these first. These ones right here and these ones right here. And those are the easiest ones to talk about. So that's what example 1 is about. So here we go. I'm going to erase these. I hope you got them down. You can pause it. You probably already have. Because I've only got so much board space here, and that's when I have to keep erasing. Okay. So the very first instruction in example 1 says, describe the transformations of f of x equals x squared, the parent function. So describe transformations of the parent represented by g equals x plus 4 squared minus 1. Two things are happening because I've added a number on the inside of the function before the squaring, and I've actually subtracted a number on the outside after the squaring. So this is going to move it right and left, and this is going to move it up and down. And this is how you describe the transformation. G is f of x moved left 4, because that's what happens inside, so we always deal with the opposite, and that's a horizontal move. Left 4 and down 1. It's just like that. That's just that easy. It says, then graph each function. Well, okay, get rid of my graphs over here. We're supposed to graph each function. We're supposed to graph the parent and the transformed function. So here we go. Here's the parent. You'll graph this so many times, you're going to get really used to it. You start at the origin. You go out 1, up 1, out 1, up 3, out 1, up 5. Jump across the axis of symmetry, grab some symmetry points, There's your parent graph right there. There's f of x. Okay? Now we are to graph this transformed function, which means we got to take this guy and move it left 4. So I'm going to grab it right here at its vertex, move it left 4, and down 1. So its vertex is going to be right here. And guess what? There's nothing in here to vertically stretch it, shrink it, or reflect it. There's nothing in here to horizontally stretch it or shrink it. So it's going to have exactly the same shape as that. It's just going to start at a different place. So I start here and I go out 1, up 1, out 1, up 3, out 1, up 5. Jump across the axis of symmetry, which, by the way, is located here now. Jump across that. Plot some more points. Voila. Okay? So the pink one was graphed just like the blue one. It's just it started in a different location according to these up and down, right and left movements. That's not very hard. Let's take a look at example 2. This one says, describe the transformation of the parent represented by G, then graph each function. So actually, example 2 has got two things we've got to do. Notice that the A part, where G is negative 1/2 x squared, we have the capability to do this right now without ever plotting points, because of what I've shown you so far about transformations and about a quick count. So we're comparing to f of x equals x squared, and we have a G function, which is negative 1/2 x squared. That's the A part of example 2. Two things are going on here. First of all, notice this. It's not going right or left anywhere, and it's not going up or down anywhere. We haven't added anything to x before we squared it, and we haven't subtracted anything off the back. This is strictly a vertical shrink and a reflection. That negative is a reflection. This is a horizontal shrink. Sorry, boy, did I screw that up. This is a reflection in the x-axis, and this is a vertical shrink of 1/2. So this is how we describe it if they wanted us to describe it. It would be a reflection in x-axis and a vertical shrink of 1/2. So let's see if we can make that work with the quick count that we've learned and see if we can get it taken care of. This right here is not moving right, left, or up, down from the parent, so I'm going to get rid of this other dotted one from the previous one. Fill in the gaps on this blue one so we've got the parent function again. The parent function looks like that. There's your blue one. Okay. Now how are we going to graph this that has these transformations? First of all, it's going to open downward. It's going to open down. It's going to open like this because of this, the negative right here. And it's going to be fatter because this is a vertical shrink. So watch how I do this. Try to pay attention. Start in the same place because it didn't move right, left, up, or down anywhere. And I'm going to go out 1, down 1/2 because of that 1/2. I'm going to go down 1/2 as much as I normally would. Then I'm going to go out 1, down 3/2 because the next odd number is 3. And there's a 1/2. There's another 1/2. Sorry, let me try that again. Come out here to this 1/2, and I want to go down 3/2, which is 1 1/2. 1 1/2, there's 1. I'm sorry, 1/2, there's a whole one. So right there. Then I'm going to go out 1 and down 5/2, which is 2 1/2. 1 1/2. And if I wanted to do one more, I would go out 1 and down 3/2, which is, 7/2, which is 3 1/2. There's my 1/2. 1, 2, 3. Jump across the axis of symmetry. Grab those same points. Oh gosh, follow the line, Johnson. Okay. And we get one that opens downward, reflected over the x, and it's fatter than the original by 1/2. Okay, and you can do it really quickly if you understand these, how to count those transformations. Okay, here's the next one. B part. It says g of x is, in parentheses, 2x squared plus 1. So the new g for the B part after transformation is going to be 2x in parentheses squared plus 1. Okay, so how are we going to describe this? Well, This happens inside. Since it happens inside, it will be horizontal something, and it will be reciprocated. So this represents a horizontal of 1/2, because that's the reciprocal of 2, and it's also up 1. Horizontal shrink of 1/2. How are we going to handle that? I'll show you how we're going to handle it, and the book doesn't show you to do it this way, but it'll still allow you to graph the graph really, really quickly if you follow what I'm doing. I want to do a little bit of work on this so that I can understand a little better how I'm going to count it. So watch this. This g of x is exactly the same thing as, if I were to apply that square to both the 2 and the x, I would get 2 squared x squared plus 1, and I no longer need the parentheses, and 2 squared is 4, so I have 4 x squared plus 1. This, in the squaring of it, has become a vertical stretch of 4. This is what I said the other day when I said a vertical or a horizontal shrink of 1/2. Same size transformation as a vertical stretch of 4, which is what we really have here. If you transform this function so that you can see a vertical stretch, then you can count it the way I told you. What this thing's going to do is it's going to start up 1 from the parent, which is right here. And this 4 right here that has now become a vertical stretcher, this 4 right here is going to be how many times we multiply the next odd number to count up. So I would go out 1 from the vertex, which is up 1 right here. Go out 1, not up 1, because that's what would be what we would do normally. We're not going to go up 1, we're going to go up 4 times 1. 1, 2, 3, 4. So this is quite a stretch here. And then we would go out 1, not up 3. That would be the next odd number as we went out, but 3 times 4, which is 12. 2, 3, 4, 5, 6, 7, 8, 9. And you don't need to go beyond that, because that's real. First of all, I'm not tall enough to count that high, and it's a really big number. So this will be enough to give us an indicator of just how skinny this thing is. It's also been moved up 1. Okay, so there's a graph of that one right there, which is, you have to describe it when you do this, especially on Big Ideas Math. When you have to describe this as a horizontal shrink of 1/2, because as it's presented, it's inside the parentheses. So you have to describe it this way. But you can transform it into this so that you can do your quick count by squaring the 2 and getting a 4 for a vertical stretcher. So don't call it a vertical stretch of 4, though that is what it is. Call it a horizontal shrink of 1/2, because that's how it's presented. Okay, now we're going to have to go backwards. What they're going to do is give us a description in words, and we have to write down the transformation that occurs because of it. All right. In example 3, it says, the title of it says, writing a transformed quadratic function. It says, let the graph of g be a vertical stretch by a factor of 2 and a reflection in the x-axis, followed by a translation 3 units down of the graph of the parent. Well, that's quite a mouthful. That's 3 transformations. We have to do them in order. So just a reminder, this is our parent. And I'm going to have that intermediate stuff, like I always said, I always do that. I'm going to have this h of x, and we're going to do the first bit of transformations that they want us to do, and then we'll apply the last one to h. So it says, let g be a vertical stretch by 2 and a reflection in the x-axis. There's going to be more to it, but that's the first thing I want to write down, and it looks like this. That's vertical stretch of 2, reflection in the x-axis, both take place outside the function. There's x squared. So that's the first 2 things they ask us to do. And then followed by a translation 3 units down. So we're going to take this h that we've got right here, and we're going to move it down 3 units, which would be f. No, sorry, my mistake. Blew that, hang on. This last function I'm going to write is going to be the intermediate function down 3. So it's going to be negative 2x squared minus 3. And you could have probably done that without all these intermediate steps. But again, we want to practice this intermediate stuff on the easy ones so that we can apply the same method to the harder ones. So this has been reflected over the x-axis, vertically stretched by 2, and moved down 3 from the parent. That's what they asked us to do in that order. Okay, so you have to follow the words and write the transformations in an equation. Okay, moving along, let's take a look at example 4. This is the worst possible kind because we're not going to be transforming the parent. We're going to be transforming a daughter into something else by following the words. A daughter function. So take a look at example 4. It says, let the graph of G be a translation 3 units right, 2 units up, followed by a reflection, blah, 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 of f of x equals x squared minus 5x. So again, this is one of those where they gave you the function you're going to transform. They give it to you at the end of the problem. So you got to read through to find the function you're going to do, write it down, and then read the transformations again. So f is x squared minus 5x. So it's not the parent this time. It's also a rather strange looking quadratic because you're not used to seeing quadratics presented this way with a squared term and then an x term. So this is new. This isn't like doing something to x squared and adding, subtracting something inside before you square it and all that. They've got an x term here now. Still quadratic, characterized as quadratic because of this square term right here. But this thing is weird. This has got an x which occurs in this term and also an x which occurs in this term, and we got to be really careful with that. So I'll focus on that as we go through it. Now that we found our function we're going to transform, we've got to go back up to example 4, or to the reading of example 4, and it says, let the graph of G be a translation 3 units right and 2 units up. It's going to be followed by something else, but I want to handle that right now. So I'm going to have this intermediate h of x, and it's going to be this f, which I'm not willing to deal with in a specific way yet. It's going to be 3 units right, 2 units up, meaning it's going to be f in a general way, 3 units right, 2 units up. Okay, so we make that general to f. We've not approached this thingy at all yet. We're just going to do this right here. That's all we're doing to that right there. Now we're going to write G in such a way that it says followed by a reflection in the y-axis, which means that G is going to be H reflected in the y-axis. That's how you do a reflection in the y. It takes place inside. So what does that all mean? It's really hard to put this all together now. What it means here is that G is going to be H of negative x, means go back up to H up here and replace all of its x's with a negative. So we're going to write f of negative x minus 3 plus 2. Okay, so we replace this x in H, because that's what it said to do. Replace this x in H with a negative x. Everything else remained the same. Now, this thing right here, now I've got to keep backtracking up here. This thing right here, that is going to replace all of the x's in f. So the final function looks like this. There's still going to be a lot of work to do on it. This is a hard one. It's going to be negative x minus 3 squared. That's this part right here. It's replacing this. Minus 5 times negative x minus 3, because this x also gets replaced with what's in this parenthesis. And then plus 2. That just tags along the end there. Now, unfortunately, you cannot leave it this way. You got to clean it up and fix it up. So, first thing we got to do is square that binomial. This is going to be tough with all those negative signs, so stay with me. I want to square negative x minus 3, which means to write it twice and FOIL it out. So I have negative x times negative x, which is positive x squared. Negative x times negative 3, which is positive 3x. Negative 3 times negative x, which is positive 3x. And negative 3 times negative 3, which is positive 9. So I end up with x squared plus 6x plus 9 when I combine my terms, and that's what this has become. X squared plus 6x plus 9. Now I've got to distribute this negative 5. There's no squaring out here. I'm just ready to distribute, which gives me positive, because it's a negative times a negative, 5x a positive 15 and a positive 2, that one tagging along the end after I distribute the negative 5. Now I got to combine all the like terms. There's only one squared term, so that's x squared. I have 6x and 5x, that's 11x. And I have 9 and 15, which is 24, and 2 is 26. If you take a look at the final answer in the solution, we get x squared plus 11x plus 26, which is what we finally got here. That's tough. And I'm not going to have you do too many of those problems, but if you end up with a function that has an x squared and an x term and possibly a constant back here, and you have to transform it, you've got to go really, really slow. And then when you finally get a g of x function, you got to clean it up algebraically, which you learned in Algebra 1 and geometry. So you may want to refer back to this when you get to the really, really tough ones. The last thing that we're going to do is example 5, and it is rather interesting, something you may not expect. What I'm going to do on example 5, you got to give me just a second, and I'm not going to stop this because I'm not sure if a pause will turn it off or not. But what we're going to do is going to be a calculator exercise. So let me get the calculator out. There's a calculator display out here so you can see it. Hopefully that'll be something you can get to. Oh man, that's so glary. Hang on. See if I can prop this up and get the glare off of the screen. I might be able to turn that. No, I can't turn the front one off, only the back one. Maybe. Hang on. Let me see if I can just turn off these lights. That might show up well enough. Let me try my calculator and see. And if it doesn't, then we'll do something else. Just a second. Should have had this out before I started the video, but I forgot I was going to have to do this. Sorry. So just hang in there with me for a second. Okay. Hopefully you'll be able to follow me on that. I think you will because this thing's lit up. Hopefully the light will show up well enough. Okay. So example 5 is rather interesting. Here's the scenario. You can read it with me. You probably should, so you can go back to the words that I'm going to go back to. Page 51, example 5, says the height h in feet of water spraying from a fire hose can be modeled by h of x equals negative 0.03 x squared plus x plus 25. Well, that's a quadratic. Probably doesn't mean much to you because all those numbers are difficult to anticipate and interpret. But anyway, it can be modeled by this. The height of any bit of water can be modeled by this, where x is the horizontal distance in feet from the fire truck. And so the crew is going to raise the ladder so that the water hits the ground 10 feet further out from the fire truck. Write a function that models the new path of the water. So this is pretty crazy. Let me push this out of the way a little bit right now and just talk to you about, hopefully you'll be able to see on the chalkboard what's going on. What we've got here is this. We have a fire truck, and they're shooting water off the ladder right now. Let me turn the lights back on. I hope you can see that without too much glare. So the fire truck's sitting over here like this, and he's got, I don't know, this is the back end of the fire truck right here. Here's the wheels. And this guy's going to, there's a ladder stretching up like this from the fire truck, and there's a guy standing here, and his hose is firing from here. Well, maybe the ladder goes up like this so that it hits the y-axis here. This is where he's shooting from, and the water follows a parabolic path like this, and it hits the ground over here somewhere. What we want to know is how much will we have to change this height right here? This is h of x. By the way, this is the horizontal distance across the ground. This is the x-axis. This is the h of x axis. We call it the y-axis. What we want to do is be the firefighters, and we want to raise this ladder up so that where we're shooting it from is higher, so that when the fire, so that at the same angle here that the guy fires at, it actually hits over here, so that this distance is 10 feet further than it's hitting now. That's what we're trying to do. How are we going to do that? Let me show you with the calculator how we can anticipate this. But you got to really understand what it is we're after before you understand what I'm going to do with this calculator. Try to point it all out to you. You can review it as you, because there's a couple of problems I have where things are flying. There's a flying fish problem and a kangaroo, much like this water follows a parabolic path. This is how you tackle a problem like this. First of all, go to your y equals screen. That's right here, if you'll remember. Up in the upper left corner, the y equals screen, and type in the original function, which is negative, the negative sign, remember, 0.03 x squared plus x plus 25. Oh boy, that's really, really bad, isn't it? Can hardly see anything. Oh, that's going to be pretty tough. Wish that would work better here. Hang on just a minute, I might be able to try something else. Oh, hey, look at that. Shows right up. That's great. Guess we better leave the lights on. Sorry, you might have to deal with a little bit of glare. Oh, and I see it's all backwards because... oh boy, this is not going to work out very well unless you can read backwards. Maybe you can take a look at this. Let's see. That doesn't work much either. Crap, it's all backwards. Anyway, you get it typed in there. Hopefully, gosh, that's terrible. Get it typed in there like that. Maybe I can show you what's going on with the graph. I think you can graph the function. It's all backwards, but maybe you can figure it out. That's terrible. Anyway, so now what we're going to do, I guess I'll go ahead and use this since it's a little bit bigger and it's backwards, but the graph will turn out proper, I hope. So now we have to figure out a way to fit this into the window. When x is 0, meaning there's been no horizontal distance, there's been no horizontal distance yet with the water, the height is 25, because when x is 0, these two terms go to 0 and it's 25 up, which means that the height of the screen here, this distance here from here to here has got to be at least 25. And the water is going to go up from there. So I'm going to go to the window. Oh, brother, that is so backwards. I'm so sorry. The window, we're going to go to the y values. I'm talking about the vertical values. So I'm going to go to the y values. I'm going to start it at, let's say, 20. So we've got a little bit of a buffer zone on the bottom. And I'm going to let the y maximum be, that water's going to go up a ways. It's going to 25 feet. I'm going to go up to 60 feet just to see if that'll fit. And I'll adjust it if it doesn't. Between 20 and 60 is 40, so I'm going to count by 5. So that'll give me 8 tick marks. Now, what about the x's? Well, you have to think rationally about a fire hose. That stuff fires hard and fast, and it goes a long, long ways. So I'm talking about the horizontal distance now. It starts at 0. I'm going to start at -5 just to give my, so I can see the x-axis or the y-axis. And I'll leave the maximum at 60 also that I have right here. 5 to 60 is, I don't want that many tick marks, so I'm going to count by 10s. Now, let's see. That's my graph. Let's see if I get anything. Oh, that's not too bad. That's not too bad a graph. I have a lot of wasted space up here. Maybe I'd want to increase that or fix that. So here's how you fix it. I've got a lot of vertical space up here. It looks like it goes 20, 25, 30, 35. Doesn't go much higher than 40. So I'm going to adjust my window and let my y's only go up as high as 40. Y maximum. And it looked like I had about half the wasted space out here, so I'm going to have this go out to maybe 40 also. Well, that's a little better. I may want to adjust it a bit. but I've used up most of my screen, which is good. Okay, so here's what's happening. The guy's firing the water from right here. It follows this path, and it hits the ground right here. That's at 10. Remember, we scaled it by tens? 10, 20, 30, not quite 40, about 37 or something. Well, it would be really nice. Oh, you know what, though? Ooh, I'm going to have to see the ground. This isn't the ground. This is 20 feet up. Ooh, I got a lot of adjusting to do. Sorry. So I'm going to go back and let my x's, my y's, instead of starting at 20, I got to start at like -20 so that I can see the x-axis. Let's see what it looks like now. Because I got to be able to see the ground. And see, the way I shrunk this down, it doesn't hit the ground. So I got some more adjusting to do. I got to go out quite a ways more on my x's. So instead of 40, I'm going to go out. That's better. Okay, and it's hitting the ground, it looks like. If you remember how we counted these, we counted them in tens. It looks like 10, 20, 30, 40, 50. It looks to me like it's hitting right at 50 degrees or 50 feet out from the fire truck. How could I find out that value exactly? Well, this is going to be a new thing you have to learn on your calculator, so pay attention to this. To find this value right here, it's called a zero, where it hits the ground, where it hits the x-axis. And you go second, that's the blue function, and calc, that's the trace key. So it's this one, second function, and the one right next to the graph key, trace. And the second thing you see there is zero. So hit zero, hit enter, and it takes you back to here, and it's asking a question. I know you can't read this unless you can read backwards pretty well. That says left bound. It means, please provide me, I'm the calculator, I want to do this for you, but please provide me with a number that's to the left of what you see here. And we thought that was about 50. It might be 51.2, and you can't tell the difference. But we know for sure that 40 is to the left of that. It's near it, but very clearly to the left. So we're going to actually type the number 40 in and hit enter. And it puts a little arrow right up here saying, does that visually look like where you wanted me to be? Yep, that's to the left. To the right would be 60. For sure, this is to the right. 60 is to the right, but close. So now it's asking you for a right bound. So now you type 60. Enter. And the next thing says guess. We never guess. Right when you get to guess, just hit enter one more time. And it will go right to the 0, which happened to be exactly 50. So we were right in our count. But sometimes it's like 50.4 and you can't tell the difference. So you need to get it to tell you where it is. Why is that important? Why is that 50 important? Because I need to know where it's hitting right now, the water's hitting right now, so that I know how much 10 feet out is. 10 feet out from 50 is the number 60. You go, okay, I get that. Still, it doesn't tell me how high to raise this in order for it to fire from here and come out and hit 60. But I do know that that's where I want it to hit because it's 10 feet farther out. Now here comes the real clever part. If we wanted to hit at 60, what we need to find out is how far down the water is down here, not the water, but the parabola. How far down the parabola is when it is 60 out, because that's how much I'm going to have to lift the whole thing up so that it hits at 60. I need to find out where 60 falls down here, because if I can figure out that distance where 60 is on the X, that's how much I can lift it up. And I can do a vertical stretch or a vertical move with the transformation. That's not very hard to do. So what I got to do is find out on this graph, what is the Y value down here when X is 60? And I don't think I have quite enough room because look, if I visually drop down 60, I'm dropping into this region down here, which I can't see. So I'm going to do one more thing. I'm going to raise this up in my window so that this thing drops down further and I can see it better. To raise this thing up, I have to have the minimum Y value be farther down. So I'm going to go to Y, or to the Y minimum, and I'm going to let it be -40 instead, so that the X-axis will be right in the middle and I can see that fall off. Okay, so here's the 50. We agreed that that was 50. We found the 0. If I come out here to 60, what I want to do is find this point right there, right below the 60, and figure out how far it is from here to here, because that will tell me how much to raise up this entire graph so that it hits at 60. I've got to raise the whole thing up. So how do we find out that value? You've done it before. You've probably forgotten when you were doing the linear regressions. But you go second again, second function, calc key next to the trace, and choose value this time. What value? It goes back, you hit enter. What value comes back to this screen? You hit the number 60, because that's the x value we want to find the y value for. And it's negative 23. That's what we have to add. Look at what happens if I do that. Remember the number 23. If I go back to my y equals screen, and I go to the end of my function, and you don't even have to do anything to it. All you got to do is add 23, because we want to lift it up, 23. So I'm going to add, just right on the very end of it, I'm going to add 23 and hit graph. See, we didn't see this part because it started up here, and it went 10, 20, 30, 40, 50, 60. Right there at 60 is where the graph now hits. So we have gone from hitting at 50 to hitting at 60. We have moved the water out that far. How high did we have to raise it? Go back to your y equals screen. We had to raise it 23 feet. To raise the ladder 23 feet to get the water to hit 10 feet farther out. Here's what it says. If we go back, it says the crew raises the ladder so that the water hits the ground 10 feet farther from the fire truck. Write a function. Oh, we haven't written the function. Write a function that models the new path of the water. I'm going to move this out of the way. The function that we had before was the one in this y equals screen, which was, this is what we had before we raised the ladder. H of x equals, it's in the y equals screen, negative 0.03x squared plus x plus 25. That's the one we had before. This is the one we have now. It's 23 feet up. I mean, negative 0.03 x squared plus x, because nothing happens to these. To move it up, all I have to do is add a number. We did, it was 23. But I need to combine it with this constant here. 23 and 25 is 48. So this new function right here will cause the water to land 10 feet farther out. Now you might think, do firemen actually do that? No, they don't. This is for you, but this is a way in the graph. I've got this graph right here. Just really quickly, let me graph the original. I'll show you the difference. Negative 0.03 x squared plus x plus 25. This is the original. So let's compare the graphs. Here's the original right there. This is the augmented one. If you wanted to see the whole thing, if you wanted to figure that out, you would have to raise the y values up to maybe 80. So this is the augmented. This is the one we fixed. This is the original. Notice the original hits at 50, and our new one hits at 60, and we've raised it 23 feet to where this y value is now 48. That's what we put in the actual function over there. Very interesting problem. If you turn the page, if you're following with me, you're back to the exercises now. You've learned a lot. Hopefully you'll review this and be able to finish the assignment. For those of you doing it on paper, the assignment is 1, 2, 3 to 39 odd, 43, 45, and 46. Okay? Good luck with that. I will be back on Wednesday. I will talk to you about any problems and issues you have then. Happy calculating. Bye.